Automatic Bugfinding for the Blockchain, Felipe Manzano y Josselin Feist. En esta presentación se discutirán los aspectos técnicos de la Ethereum Virtaul Machine y se mostrarán los errores más comunes que tiene. Además, se presentarán dos herramientas que desarrollaron para facilitar la auditoría de smart contracts, ya que la introducción de las ejecuciones de smart contracts, como por ejemplo en Ethereum, introducen nuevos vectores de ataques que están siendo explotados en estos tiempos. Felipe Manzano es investigador de seguridad y se dedica a escribir herramientas para la ejecución simbólica de programas binarios. Josselin Feist es ingeniero de seguridad en Train of Bits, donde trabaja en el diseño y la implementación de técnicas de análisis de programas.
Also, hi everyone. So we'll talk about vulnerability in a smart contract. So first, who we are. So Felipe and myself, we are both security engineers at 12 bits, and we are building stuff, and we are looking for vulnerability into program. So the plan for today is first, we will see what is a blockchain, and in particular, what is the Ethereum blockchain. Then we will discuss on what is a smart contract and how it is designed. From this, we will look into the vulnerability side of smart contract. And then the second part of this talk will be about our contribution, which is the design of symbolic execution on top of smart contract. So the Ethereum blockchain. Behind all the hype, what is a blockchain? If you think about it in a very high-level perspective, a blockchain is just a distributed database where each participant stores all the data. To avoid disagreement, the blockchain uses a consensus protocol which ensures that everyone agrees on the data inside the blockchain. The blockchain was created alongside with the Bitcoin. So the Bitcoin is a digital currency based on the blockchain, and in particular, the use of the blockchain solved the double spending problem, which was a big issue to apply a decentralized digital currency. A few years ago, some people came with the Ethereum project, and what they did was to extend the concept of blockchain and to store within the data code and execution of the code to one application directly on top of the blockchain. You can see the Bitcoin as a distributed database, and you can see Ethereum as a kind of distributed virtual machine. So inside an Ethereum network, once one node says that Bob ran a function and the function returned 32, once the consensus is reached, everyone will agree that Bob executed the function, and everyone will agree on the outcome of the execution, which was 42. An application on top of the blockchain is called a smart contract. So everyone executes and verifies the outcome of the execution. It is decentralized, meaning that nobody can stop or prevent the execution of a function, and nobody can secretly change the data inside. This feature ensures some strong property about your application and what kind of application can take advantage of this feature. The first one is the digital currency. So basically you can build the equivalent of Bitcoin on top of Ethereum using smart contract. But you can think of other kind of application. What we found is that people for now are using it to build some kind of crowdfunding system. The ICO are one example. An ICO is a way for a company to raise money in exchange to some tokens that will be usable within the application once the application is deployed. You can also find some gambling application like poker and lottery on top of Ethereum. From my point of view, people are still waiting to see some kind of killer application, but yeah, we are still waiting for it. Anyway, the thing to know, to remember is that there is already a lot of money invested into smart contract. I just put two recent examples of people that were raising money to deploy and create a smart contract, and you can see it's like billion of worth of Ether, which is kind of interesting for something so new. So what looks like a smart contract? Ethereum runs EVM bytecode, and Ethereum wants EVM bytecode, and inside this bytecode there is not so many instructions. There is like a few hundred of it. There is one register for the program counter, and everything else is handled within the memory or the stack of the virtual machine. When you call a function, you have to send it to the network. So you have to create a transaction with a function and send it to the network to tell to everyone that you are executing this function. It's called a transaction, and each transaction has a cost. It's called the gas of the transaction, and you pay in Ether, which is the currency of Ethereum. So when you want to call a function, you have to pay. Something which is very important for us is that the bytecode cannot be updated. Once you put a smart contract with a vulnerability inside the blockchain, you can't update it, meaning that it's forever and cannot fix the bug. So people are not writing smart contract in EVM bytecode, they are using high-level language. The most famous one is Solidity. So Solidity is a kind of JavaScript style language. It looks like JavaScript. The contract is organized as a set of functions, and what is called the state of the contract, it's the contract variable, kind of global variable of the contract, and its balance, its number of Ether. So here you have an example, a contract which is called bank. So you have one state variable which is called balance. It's a map between an address and a value. The first function, which has the same name as the contract, bank, it's the constructor of the contract. This function is only called once when you deploy the contract. So usually it's used to initialize some value like the owner of the contract and so. This function is a classic function just to transfer from two users some money. And this is a specific function which contains the attribute constant, meaning that this function will not change the state of the blockchain. So you can run it locally. You don't need to call a transaction. You don't need to use a transaction for it, and it can be gas-free. So just a recap of everything. So when you call a function, you have to do the transaction, and inside the transaction, among others, there is 3 parameters: from, to, and data. From is the caller, to the construct destination, and data. The data holds the function signature, the function ID, and the parameter of the function. The way it is working is that you have to build a function ID of the function that you are calling, and you are using the hash, the first 4 bytes of the hash of the signature. So if you want to call transfer with this parameter, first you compute the hash of this, you take the first 4 bytes, you put here, and then you put the parameter. And this is the data that you are sending to the blockchain. Just an example. So, how it looks like. The first thing is when you run a contract, there is a dispatcher which will try to match the function ID with the function of the contract, and if there is a match, it will call the function. A contract can possess a default function, and this function will be called if there is no match, or if you are sending Ether to the contract. So when you are sending Ether to a contract, you actually could call some code. So just to show you. So this is the function, and it looks like assembly code and the classic one. Okay. So let's talk about vulnerability inside smart contract. The first thing to know is that vulnerability and exploit inside smart contract have already cost a lot. I just put two recent examples. So the Parity wallet, which took place like 2 months ago. So some guys managed to steal 13 million worth of dollars. And the funny thing of this hack could have been a lot worse, but during the hack, some people just realized that something was going on. and they use the exploit to attack other vulnerable contracts. They stole the money, and then they give back the money to the owner of the contract. So basically, they prevent the attacker to make more damage, which was kind of interesting to follow. We don't know who was this guy, but I guess thanks to them. The second one, the DAO hack, which is the most famous one, it took place last year, and at the time, this hack was so big for the Ethereum community that they decided to go back in time and to cancel the transaction leading to the exploit, which was kind of really complicated and have some consequences, because when you are using a blockchain, you put all your trust inside the data. And if you think that you can at some point just go back and remove some transaction, it's not so easy. And because of this hack, because of this idea to go back in time and to remove this transaction, the Ethereum community split in two, and an hard fork of the blockchain took place, and now there is two Ethereum blockchain because of a hack. So you can just imagine how important and what kind of consequences, not just about money, but like even in the trust of your blockchain you can have because of vulnerability. But what kind of vulnerability are we talking about? You can find what I call classic vulnerability, integer overflow, integer underflow, this kind of stuff. You can have waste condition because you are playing with the network. But something I think it's really like deadly and really difficult to find and to analyze is the vulnerability inside the logic of the contract or inside its design itself. Because this kind of stuff can be like not so easy to understand, but still have a lot of impact. If we look inside the DAO hack, so it was a contract. Inside this contract, you can store some money, and at some point, you could just decide to withdraw your money. You have this function to withdraw the money. What it just does, it's sending to the caller the balance. So the guy put 100 Ether inside and just said, okay, I want to have back my money. And then at the end, he put the balance to 0. But the thing is, if you remember, when you are sending Ether to a contract, the contract can have a fallback function which does thing. And in this case, the fallback function was just calling back the original function. And so you call this function sends Ether to the contract and call the fallback function. The fallback function call again this function, and so. And you can repeat this n time, and at the end, you will be able to withdraw n time your original deposit, which is pretty bad, obviously. Note that this vulnerability with the new interface of Solidity should not happen again, at least I hope so. The parity wallet hack. So there was this library which was used by a lot of contracts, and it had this function which was used to initialize the owner of the contract, but the function was public and was callable like many times. Because of that, anyone could call this function, become the owner of the contract, and just after withdraw all the money inside the contract. I just put a bunch of other examples of vulnerability you can find. I like this one, the Rubik's Cube. So I think the guy just at some point copy and paste some piece of code from internet, from GitHub, I don't know where, but he built this contract like this, and he forget to update the name of the constructor. So the constructor did not have the same name as the contract, and because of that, the constructor was not a constructor, it was just a public function. The public function was initializing the owner of the contract, and because of that, anyone could become the owner of the contract. The rock, paper, scissors is an example of what you should not do in a blockchain. So right now, all the data inside the blockchain is public. So if you build a naive implementation of the rock, paper, scissors game, when the first player play and the second player play, the second player play can know the move of the first player, and so it can always win. You can even find some really like simple stuff, like the guy just mistyped between two variables, and because of that, the contract is broke, and you cannot update it, so you have a vulnerable contract which is broke, and yeah, that's it. You can't do anything. So what I wanted to tell you is that This kind of vulnerability, it's different than memory corruption when you can say, okay, there is a crash and so. It's more difficult to find. You need some understanding of what is a contract meaning. And yeah, it really depends on the purpose of the contract, because you have this example where an attacker ends with more money than he invests inside the contract. Is it a vulnerability? Is it because of a vulnerability? If the contract is a prepaid service when you just put money and receive an object, yeah, it looks like a vulnerability. But if the contract is a gambling application or a lottery or even a bank, it's not necessarily the case. It really depends on what's going on. So yeah, this kind of detection of vulnerability, you really need at some point the user inside the loop to know what's going on.
That's me. So, smart contracts are small programs that handle a lot of money and have bugs. So we think that maybe applying symbolic execution to try to analyze those is a good fit, so we did. We already have a symbolic execution framework that works for Linux programs, so we implemented this EVM module that let us use the same framework to analyze EVM code. Basically, we did a symbolic execution for EVM. So in this symbolic execution thing, all the contract paths are explored. Our framework supports multiple contracts and transactions. And well, it produces the input needed to reproduce whatever fail it may find. And it has this API for basic generic instrumentation. You can run a contract concretely and check for some dynamic conditions on the trace and stuff like that. So how this is done? As usual, the input of the contract it's considered a symbolic expression, not a concrete value, but an expression that represents all the possible values given by the representation of the value. Then the emulated instructions of the machine are going to build these new expressions based on the symbolic input, and eventually, if you need to make a choice that is based on one of these symbolic values, you basically copy the state of the framework in a number of times, and in each of the instances, you add the necessary constraints to describe the input needed to go that way, and in all times, you have this Oracle type thing, this black box solver, which is an SMT solver that you use you query it, you ask it to solve this set of constraints, this math you are building over the execution of the contract or program. So let's consider this super small program and contract. What it does is to simply check that it won't have the dispatcher as we were talking. It will be just this function, and it will take the input and check that it simply checks that the first byte on the input will be equal to A, and if it's not, it will do a different thing. So at the beginning, we have like nothing in our path constraint, but when we get some input, we will have like a free 8-bit bit vector that will represent all possible 256 values. The program will then progress and build these symbolic expressions over the free byte, and eventually it will reach the if statement. In which case, this thing will have to make a choice over this symbolic value, and as this symbolic value could take different concrete values, the state of the framework is forked in two in these cases. In each of the instances of the analysis, we add the necessary constraints to represent whatever is needed to go each way. In this case, we'll simply add the constraint of the message being equal to A or different to A. So at the end of this, we will get not just the concrete example of what we should feed the original program to reach this spot in the program, but also the complete, let's say, math representation of all the inputs that will let you do that. So in this case, in the case of the all but A, we will get like a constraint set that will represent all the letters but the letter A. So that's pretty much more or less what symbolic execution is about. So for any of this, we need a pretty good, well-coded emulator, because you have to have all the semantics coded in the emulator for this thing to work. So for doing that, in Ethereum, you start with this yellow paper. Is well known. This is where all the semantics of all the instructions and how the network works is. So you start with this. You have these are the instructions. I'm going to flash the instructions to you, so you have this. I don't know. I would like to see all the instructions before I get more into it. So there are like 60 instructions. There are a bunch of those that deal with the stack. A bunch of those that lets you deal with a memory. The machine will have an arbitrary length memory, a byte addressable. You pay more when you use more memory, so it's not really arbitrary length, but then you have the instructions that lets you jump and make loops and control the flow. Then the arithmetic ones, then the normal ones. There is a special instruction that lets you calculate the SHA tree of a buffer. And then you have like the concept of transactions inside the VM. So from a contract you can create another contract, or you can call another contract, or you can call itself. So there is like this call stack of contracts. So these are the instructions that actually like brings the notion of transactions to the EVM assembler. So all of the instructions deal with the stack. It normally takes some values from the stack. It does something, and eventually it dumps the result on the stack or in other of the parts of the VM. In this case, this will try to store this value into this address. So it will take the two values from the stack, and it will just write the thing into memory. It will use big endian, and the values are 256 bits long as normal. What else? So for a transaction, everything starts with a human issuing a transaction over the network. So you need accounts. There are contract accounts and user accounts. The contract accounts are simply accounts that has some code associated with it, and some storage, which is some kind of database that is associated with the contract account. So from the user will log into the network and issue a transaction. It will try to call this contract. So the thing that happens there is that the code associated with the contract is then instantiated in one of these VMs, and you always start executing on address 0. So the thing starts executing and doing its stuff. For example, call value is, there are instructions that lets the program read the input of the transaction. So this symbolic stuff is maybe starting there, but eventually it can call. Well, eventually it will modify its own storage. So the result of executing a contract will be to some modification on its own contract. It cannot modify a storage of a different account. It only can modify the storage of its own. So this will advance, and the storage there it will modify itself, right? So eventually it also could call another contract. In this scenario, we have only one contract in the whole world, so it will call itself for some reason. It will call itself, so another instance of the VM will pop up the other one, and you can do this a number of times. There is a limit for it. I think 1024. So for doing this symbolic stuff, at some point we need to be able to copy the whole state of the analysis, and in particular the state of the Ethereum world. So we need to get all the other stuff and copy it on a number of times. In each of these, we will do we will maintain the path constraint or the constraint set, which will be a little different in each case. So some words about contract creation. When you take this Solidity source code and you compile it with the compiler, you get an initialization bytecode. This is not what is going to be associated with the account, but an initialization bytecode. And you run it, and what it's supposed to do is to initialize the storage, and also gives you back the actual runtime bytecode. So it will return the actual code that will be associated with the account. And then this is kind of difficult to learn from the internet at the beginning. But it was for me. If you want to pass data to the constructor, you need to append it to the bytecode, initialization bytecode. So let's try our tool with against the most simple possible example we could think, which is this one. So there is a Python script. The whole Manticore EVM framework is written in Python. So you start with this script. You instantiate the Manticore EVM framework, and then you start creating the accounts. You need to. So it starts by nothing. So you have to with nothing. So you have to create all the accounts. You have to set up the initial world you are trying to analyze. You have to, whatever you're trying to do with this, you need to recreate this on the framework. So you create, for example, a user account. You compile some source code. The one from the other slides would be better for this example. And you actually run the initialization bytecode, and this will create the account and associate the code with the account and initialize the storage. So eventually, finally, we will have two accounts set up in this emulated Ethereum world. Then we need to throw transactions to this, and we do that. This is why we needed two accounts, because we needed someone to actually, a user trying to recreate what is going to happen in the real world. the user account is used as a caller. Then the address, which is the destination of the transaction, is the contract account. And then we set the input of this transaction as symbolic values. So we don't put here like a concrete value, but as a symbolic value. And then, so eventually, as the input is symbolic, the framework will find not a single final state, but a lot of different states, because it eventually find the if statement and fork the situation. And so at the end, you get all there is to know about the contract. Basically, the input needed, examples of the input needed to go to each of the branches of the program, and the coverage, and that's it. So in this case, we get two interesting states, because the program was super simple, and in one of the states, we simply have the first byte different of 41, and in the second, the actual 41, which is the A, that will be the one that goes to the A. This, of course, is a simple example, and we could get much more, this thing works in much more complicated stuff. So, consider this integer overflow thing. This example, a difference from is a little different because it has the function, so it will have this dispatcher at the beginning that will try to match the function ID and divert execution to the function add or to the default function and those things. So in this case, we start with a storage variable in 0, and then there is a function that will add whatever you pass to it to the storage variable. So this has the problem of the overflow, but the idea is like for an auditor to simply this will be like a complicated math. It's not necessarily this simple. It could be like something super complicated, and the human reading this will I don't know, get in doubt about this operation, and then he or her could add assertions guarding the complicated operation. So that's more or less the workflow we envision. Someone sees a complicated math and puts these assertions like guarding the stuff, and then it sets all the input in as symbolic and send it to the framework. Okay, but this thing won't actually overflow if you just run add once. You will need to, because the first time there is no, as it starts at 0, there is no number you can add to 0 that makes it lower than the original, because it's unsigned. So you need two transactions. You need one that presets the seller balance to whatever value over 0, and then a second transaction that actually hits the assertion you're trying to find. So we go back to the Manticore script, and we set up the emulated world with that contract. So we set a user account. We send some. It's free here, so whatever. We send some money to them. We compile the source code, and we create the contract account. And then we run two transactions to this emulated world, right? We could have like a fully symbolic input here, but we just pre-constraining, let's say, the symbolic data to just call the add instruction, because we already knew that's where the problem is, or that's what we think it's interesting to explore. So we send a transaction with this previously constrained symbolic data in which only the value passed to the add is symbolic and not the function ID. So this thing will call the add and will set the storage variable with some symbolic value. And if you stop here, you will find out that you didn't cover all the code and didn't really hit the assertion because the overflow didn't occur. So you send pretty much a similar. It's not the same because you are generating new symbols. So both of the values you are sending could be different. So you set a new similar transaction again, and then you ask for the solution. You ask Manticore to give you the solution of it, and it will give you simply two values, two states. Each of the states describing one of the states will reach throw, which will be the one hitting the assertion, and you will have the first 4 bytes, which are the function ID, but those were concrete because we already wrote it like in a concrete value. But the second, the first parameter of that function, which is add, will be if you add these two, you will get an overflow and you will hit the assertion, and if you add these two, you won't. So it basically lets you explore complicated math and contract constructs automatically without you needing to actually go into it. This is a program that will try to what does this? This is trying to replicate a bug that we found that the init wallet one. The bug that there was a bug on the contracts on the blockchain that you could simply call a function that was there. It was public and you can change stuff. So in this contract, what you can do, it starts by setting setting an owner. The owner will be the guy initializing the contract, calling the initialization, and then the owner could change the owner, could pass the ownership of this contract to another user, and you're supposed to check that the one changing the ownership of the contract is the actual owner. But if you don't, anyone could just call this contract and change the ownership of the program. This simple thing happened on the blockchain, and you could take a lot of money doing that. This is super simple for a symbolic executor to actually find because it will simply try all the functions and eventually will hit the function that simply gets you all the money, and that's it. So from the point of view of symbolic execution, this is not super interesting, but it's something that will be easily found by just trying it. Okay, so everything is so good, but there is a problem, which is the SHA-3 problem. The problem with SHA-3 is that it is designed not to allow symbolic execution. If you have, in this case, for example, if you have a free buffer, a totally controllable buffer, and you calculate the SHA-3 of this fully free buffer, you can put whatever you want there. It won't really result in a controllable hash. You cannot you cannot really control the result of a hash over a buffer you control. You could try to modify the buffer, but you would not give me like this concrete result at the end. The SHA-tree function is devised, is designed, so you cannot really ask an SMT solver what should be the input of the SHA-tree, so SHA-tree gives me this result. So this is a problem because in Solidity all mappings are implemented via SHA-tree. So it will not work. A simple symbolic executor that reaches these SHA-tree instructions that are pretty much everywhere won't work. So we need to do something about that. What is done on other projects maybe is to return, when it happens, when you get a SHA-tree over a free symbolic value, it is replaced by a free symbolic 256-bit vector. So they assume, a solution would be to assume that you can actually control the output of SHA-tree, the output of the hash, if you control the buffer. And then that works like at the end of the analysis, you get a lot of false positives, and you will get these things and try it on the original contract and check if some of those work. But it gives you basically false positive because it's assuming you know how to control the result of the hash by controlling the buffer, the input buffer. There are other options, but what we are doing is maintaining all the currently known pairs of buffer and hash of the buffer. So we let the program run, and every time you find an instance of SHA-tree calculated over a concrete buffer, you remember the pair. So in this case, you will match this string, this concrete string, to this hash, and the program will keep working and will find a different string, and it will add another pair to this global database you have. So eventually, when you get to, this should be hash, not SHA-tree. Eventually, when you get to the actual symbolic hash, what you do is to build a symbol that represents all the potential values. So you write build this expression that will give you the first concrete hash if the symbolic buffer is equal to the first string, and you simply build this symbolic construction. So in this case, you have a mapping which is implemented with SHA-tree, so it will calculate the SHA-tree of all these things at the constructor. So at the time of the initialization of the program, we will know all the buffer versus hash matching of this thing, and eventually it will reach this. And at this point is when we need to replace the instance of a SHA-tree over the symbolic value with the special expression. So we did that, and we run it on that contract, and we get two different states. One state in which the balance key is greater than 20, and the other state in which the balance state is lower than 20. That means that we get two states. One that gets you these three values as potential inputs, and one that gives you the two values above on the other state. So we will get that. And that's kind of a nice thing to do, because now we can actually deal with mappings. And that's what I have. This is you?
Yeah, this is me. Yeah, so what we wanted to tell you is that smart contract is a new technology, but there's already a lot of money invested into this technology, while developers are not always really aware of the security implication of what they are doing. So it's kind of interesting for us as security researchers to work on this. We don't know the future, but we will probably see some other large hack inside Ethereum. And this means that definitely we need new tool and we need new solution to find and to audit a smart contract. We believe that EVM is a good fit for symbolic execution because one of the two limitations of symbolic execution is the size of a trace, of a pass, and the number of pass. In smart contracts, the twice are kind of small, and there is not so many paths. So it seems to be a good fit for it. Also, we believe that you need, at least in smart contract, you need the human inside the loop to detect vulnerability because it's not, as we said, you don't have the same detection than for memory corruption. Yeah.
Yeah. So what we need to do still on the Manticore EVM framework is to implement gas. We don't have that. We are just ignoring everything that need to fail because of out of gas exception. So that's something we should do. We have ideas on use this to basically implement a binary diffing thing. It is super simple to do once you have a symbolic executor working. You take two versions of a function that could be like the compilation with different compilers or different version of compiler of the same function. You have two flavors of the same function. You send the same input to both of them. You run it on the symbolic executor and you check for differences. Then add some AVI helpers, which may ease how you use the script, vulnerability heuristics, and maybe a meta assert instructions, so you can add this to the contract and not modify it, but look for those. So
a bunch of similar work. You can see that two of them are also using symbolic execution, which means that we are not alone believing that symbolic execution is a good fit. Some people are also using static analysis, and put the link if you are interested into this work. And thanks for your attention.
So we take all the time. So if you want to ask some questions, we go. They say there is a room over there. I don't know, but antesala. Thank you.
Thank you.